Hey guys, in this tutorial we're going to take a look at how to make tire tread in Grasshopper. So this is what we're going to be making, just a reasonably straightforward model, but it will take quite a bit of time. This could well be one of my longest tutorials to date. So let's dive into a new document and get started. Get rid of this, and okay, so we're going to start with 3 points. So I'm going to drop down 1, 2, and 3. And I'm going to throw in some sliders as well. And so the slider is going to have a maximum value of 100, and I'm going to plug that into my Z, and then I'm going to plug that into my next point component as well. I'm going to throw down another slider, maximum value of 100 again. This is going to be my X value, and in fact, let's see, so that's going to come out here somewhere, and then I'm going to make a third slider, and this is going to be this value minus this value, and that's going to be our Z, and then we're also going to plug our X coordinate into this one as well, and so this just lets us sort of move down from from that point a little bit as well. And now I'm going to put these all together in a polyline. So 1, 2, 3, and then I'm going to explode that. And now that I've exploded it, I'm going to list item out the individual curves. There's 1, and there's 2, and then I'm going to divide these curves up as well. So I'm going to use, oops, not that. I'm going to use divide curve. And so for the first one, I'll leave that as is. And then the second one, I'm going to plug in a slider. Actually, I will plug in a slider for both of these. Maximum value of 10, make them an integer slider, but they're going to have different values. So this one will sit comfortably around 4, this one will be a little bit higher. And then what we're also going to make is a range, because we're going to put down a graph mapper. So this graph mapper is going to control the shape of this horizontal curve. So it's going to be set to Bezier. I'm going to put a multiplier down as well, and set it to floating point numbers. Plug that in, and then I'm going to move in the Z direction these points here. And so now let me just shape this a little bit. I kind of want it to flatten out to some extent. Maybe something like that. But I do want it to have kind of a bit of roundness as well. So that'll do for that. And then for the second list of points, we're not actually going to manipulate them any way other than using a cull index to get rid of the last item in the list. Or actually, no, I don't even need to do that. I will just cull the first item in this list. And so that way, when I put these all into a point collection, I'm going to plug in my first list of points, and then my second list of points, and preview all of this off. Now we can put not an interpolate curve, we'll use a NURBS curve for this one, and I'll just bring in the interpolate curve so you can see the difference between those. So the NURBS curve, oops, I need to flatten this collection. So the NURBS curve is going to create this very nice smooth sort of profile, whereas the interpolate curve is going to give us this weird sort of bulging out in the corner, which is definitely not what we want for this. And also the reason I added divisions on this first curve is that we can sort of gain some control over the shaping of this corner piece. You can see if I have that at only one value, it tapers off very quickly. But if I add an even 3, that holds the shape quite nicely. and I could adjust this top one as well, but I'm quite happy with that at 8, so I'm going to keep that like that. And the other thing I'm going to do actually is I'm going to mirror this collection of points, and then I'm going to reverse that list, and I'm going to cull my first item in that list. And then I can make these into another point collection again. So this is my first list, this is my second list, and here's my NURBS curve. Alright. So that's all working pretty well. Now what I want to do is I want to split this, should we say, this profile, and I want to split it at this corner point, sort of where the surface changes direction. So I'm going to use the point that I created here. But what I'm actually going to do before that is I'm going to list item out the first point in here, and there is only one point at the moment, so you might be wondering why I'm doing this. And what I'm going to do is actually I'm going to throw another point in here just to mix things up a little bit. So we now have 2 points coming in here. There we go, 2 points. And I'm going to do a curve closest point from these points and this curve here. And then I'm going to shatter this curve into 3 pieces. So I'm going to plug the curve in, then plug my parameter to shatter at, and we should get 3 curves. Yep, there we go. So now what I can do, with this I might also just grab the end points and draw a polyline between those. Actually, instead of doing that, let me just explode it and draw a polyline. And then I'll join these curves up. So let me join that and that. And I need to flatten those points coming in as well. And now I can do a revolution surface. So I'm going to revolve this object, and my axis, my revolution axis, has to be defined by a line. So I'm going to use a line SDL, which is start, direction, and length. Let me plug that in. According to my world axis gimbal, I need to plug in an X vector for my direction, and I also need a start point, which will just be a construct point node at 0, 0, 0. And there's the base for our tire. Now, let me just go back and tweak these parameters a little bit. That is way too thick for my tire. Maybe I'll just adjust this as well. Actually, it was pretty good where it was, so I'll leave that there, and I'll continue doing what I'm doing. So now I've shattered this curve. Let me list item out the second piece. Preview that off. Turn some of this stuff off as well. And there we go, I've got our first and second one, but we're only worried about the second one. And I'm also going to do a revolution of this. And actually, what I might do is I might just revolve... Oh, no, I won't do it like that. I'm going to revolve this curve, and then I'm going to extract a subset of that curve. So I'm going to use isotrim, and this is my surface for trimming, and I'm going to bring in a domain. Let me just move this out of the way as well. So I'm going to construct a domain, a square domain. You always use square domains for surface editing. And I'm going to reparameterize the surface. And so my U domain, what we're going to be doing for this, or in order to construct this tire, whoops, did not want to group those. In order to construct this tire, we're basically going to extract a small subset of the surface, populate it with geometry, and then copy that across our entire surface. And so I'm gonna put a slider down, which is going to control my number of divisions. I'll give it a maximum value of 64, and maybe I'll set it to 32 for now. And then I'm going to take an expression, oh not an expression, just a polynomial, which will be 1 over x. So when I plug in 1 over x into here, that'll give me the section I want. And then my v domain is going to be 0.5, because I only want half the width, because once again our geometry is going to copy over across that center point. So that's my subsurface. I can preview the, okay, now I can sort of work on the definition for the tread. So actually, you know what, I don't need to turn those off, I'll keep those there. Oh, no, I will turn them off. Sorry. So now we're going to start on a different part of the definition. So I'm going to construct a rectangle, and I'm going to give it a value of 1 in the x and y. So it's going to be a square. And then I'm going to turn it into a surface. And I'm going to make 3 copies of this. So in order to do that, I'm going to construct a point, plug that in there. This will be my base plane. And I'm going to make a series. And this will be in the x direction. And I'm going to make 3 copies. So integer slider, set to 3. Doesn't even need to be a slider, it can just be 3. And now what we're going to do is we are going to evaluate the surface. So let me no, I'll keep those on. I'll keep these on. This one right here. Okay. Whoops, not disabled. Alright. So I've made that one surface. I'm going to make one more surface. And this one is going to have an x value of 3. And we only want it on the first base plane. So there we go, it spans exactly the same size as our 3 surfaces, and you'll see why this is useful in a few minutes. Oops. Okay. So let me now take these surfaces, and actually I'm going to create a graph mapper. And I'm going to set it to Bezier. And then I'm going to put a range in as well. And a number slider. Maximum value of, I don't know, 20 will do. And then I'm going to create a copy of that. I'm going to do 2 of these. And then I'm going to put down a merge components component. And I'm going to go 1, 2, 1. This is important because what we're going to do is we're going to repeat the same graph on our output as well. So now I'm going to, let's see, I'm going to graft this output here, and then I'm going to flip this matrix here. So we should have 3 lists with 11 items each. Yes, we do. And now we can construct some points. And also, actually, I'll do the flip matrix after I've constructed the points. So this is my y value, this is my x value, and this is my uv coordinate. And now I'm going to interpolate these curves. And actually I've done that the wrong way because I forgot to flip my matrix. but there we go. So now let me preview this off. Oh, that's interesting. What has gone on there? Now, right, I probably need to graph these surface inputs. Alright, there we go. So now I can tweak these end ones, and I want the middle one to do something different to the end too. So maybe something like this. I don't know, doesn't really matter. And then we're going to divide these curves, and then we're going to interpolate these points in the opposite direction. It does not matter how many divisions we do in this direction necessarily. I mean, it does matter to some extent because you will get more sort of accuracy. Well, it depends on what you're going for, but at this stage it's really not that important, because we're going to divide these curves again. Whoops. And once again we're going to flip matrix and interpolate curve. Now this is the collection of curves that's important. So we can have as many as we want in here. And I might just see what happens if I put a rebuild curve in here. It might just make my geometry a bit nicer. Somewhere around there's looking alright for me. Might take these down. Let's just work with a lower number for now. Alright, so what we're going to be doing is we're going to be joining sort of one curve to the next to create a lofted piece of geometry. And so this means that, and then we're going to sort of tessellate that across the entire surface. So what I actually need to do is I need to get rid of one of these end curves, because otherwise we're going to have two tessellated curves sitting right next to each other, on top of each other, and that's not really that helpful to us. So I'm going to flatten this output, and then I'm going to cull. Where's my cull index? And I'm just going to cull the first item in the list. So item 0, that's gone, and we're away laughing. Cool. So now that I've got these 8 planar curves, sorry, what's my next step? What am I doing with these now? Alright, I probably need to sort them into lists of 2. Alright, so at the moment there's 8 items all on one branch. At this point I'm also going to ensure that this slider type is always set to even numbers, because, actually let me just show you, if I do have this set to integers, okay, let me just do the rest of the setup first. So we're going to put down a path mapper, and I'm going to simplify this, and actually I'll graft it as well. Well, actually no, I won't graft it, because I can create null mapping. I'll flatten it actually instead of simplifying it. Create null mapping, bring in my index number, and this here is just going to be the floor of I over 2, close parentheses, and so this should give me 4 lists, each with 2 items, which is exactly what I want. And this is a key thing to note, if you only do I over 2, it's going to sort of mess with your the structure of your paths a little bit. So you always need to take the floor of whatever it is, because this is going to round it down and ensure that your data structure is working properly. Alright, so floor of I have 2. Oops, accidentally disabled there. Okay. Now we can actually, I won't do this, I'll save this for further down the track, but let me see, which way do I want to do this? I might do this now. Using this surface, I'm going to extract some ISO curves. So plug my surface in and UV coordinates. I'm going to construct points. So this is giving me, okay, let's see. I'll plug in 2 variable sliders here. I think these want to go in my Y direction. Yep, so that's what I want. I want these horizontal curves, which should be my U curves. If I just bring out a curve, oops, my U, yep. Okay, and what I do want to do is a curve-curve intersection. So this is my curve A, this is my curve B, and then I want to shatter the curves again. So I'm going to shatter these curves. Let's see, I'm going to set this to my principal data structure, and that hasn't really done anything. So maybe I'll simplify this. Did that principal? No, it really hasn't done what I wanted it to do. Whoops. Okay, we've got 8 curves here. I'm going to have to graft those, and then I'm going to have to do another path mapper over here, plug that in, create null mapping, and I think I want, well, according to this, what I probably want is B, A. So these are the parameters I'm shattering at. 2 parameters on each curve. And then I'm going to do a list item. And so that is my first curve apparently. There should be 3 curves coming in here. Oh, whoops. Looks like, okay, so when I did my curve-curve intersection, let's see what's going on. Oh, I didn't plug the path mapper in here. Okay, so my list item gives me my first curve. I'm not going to use the middle curve, but I'm going to use the last curve. So now that I've got these, let me simplify this again. And then I'm going to flatten this input and this input, plug it back into there. And now let's see what we've got on this side. So now we should have 2 curves in each list. So what I can do is I can just take the endpoints of those curves and draw polylines between them. So that will close off the start of my curve, that will close off the end of my curve, and let me just preview all these extra pieces off. This one here. I will keep, actually maybe I won't, I'll put down a join curves over here though, and so we're going to join from this curve to, let's see, maybe I don't want to flatten this, in which case let's see what's actually coming in here. And change this from AI to the floor of A over 2, and that should do the exact same thing. Yep, there we go. Cool. I'm not flattening this so that when I add it into my curve join, actually not that, I want to add this one in, and then I want to add this one in as well. So that should give me 4 closed curves. Yep, there we go. And then we're going to do the same thing with the other side, so I'll just make a copy of this and plug in 2, but I don't want this end curve. I want this to remain open for now. And so now I can merge these back into a list of curves. So this is my first set, this is my second set, and let me preview that off again, and then we'll go back to perspective mode, because now what we're going to do is we're going to map these curves to the surface. So we have mapped a surface, this is our collection of curves, this triply sized surface here. If I just go back to my top view, this is what we want as our source surface, or our base surface, and then because we multiplied, where is it? Because we multiplied this by 3 to get the size of this surface, we also need to do the same thing here. So I'm going to multiply this 1 over x by 3 and plug that into my u, and then this subsurface here is my target surface. So if I go back to perspective view, there we go. You can see this is mapping very nicely onto this surface. So now what I want to do is I want to mirror these curves, and the plane is already set correctly for me, so I don't need to worry about that, but I will join these curves up. So I'm going to join my first set of curves to my second set of curves, and this should result in 3 closed curves per each branch. Alright, so we can see our treads starting to come along. I just turn this off, I can turn this off as well now, and so these sliders over here, these control the spacing of our sort of tread marks, or like the first, second and third section, which is really neat. So the next thing we want to do is, well actually let's just try a polar array to see how this is going to work across our entire surface. So what we need to do is we need a polar array plane, which according to our gimbal is going to be the YZ plane, and then we need a number of elements in the array, which is going to be this value over here, 32 divided by 2. So because this is dividing by 2, I'm going to ensure that this is always going to be even numbers, and then I can plug that into my number here. And so there we go. There are our curves all mapped really nicely to the surface. So the next thing I want to do is, let me see, that's all working fine. Now that I've done that, I need to extrude these out. And so the way I'm going to do that is, actually, we're gonna need to trim a shape out of this curve, or out of this surface, sorry. So what I'm going to do is I'm going to create a copy of this subsurface and domain, and I'm going to disconnect my V direction so that we've got the full shape, or the full profile basically. And we're going to use this to find our normal vector. So what I'm going to do is, let's see, where is my, okay, I'm going to create a polyline from these points, and I'm going to map these ones to the surface as well. So I should have, you probably won't be able to see them, but they're sitting right along here, along the center. If I evaluate these curves, for some reason I find this to be the most difficult word to spell, or at least type in Grasshopper. Evaluate curve, and we're going to evaluate it at 0.5. And then we're going to do a surface closest point. This is our point. Our surface is this one here. And then we can evaluate the surface as well. At the UV parameter. So this gives us our normal vector. And so now what we can do is we're going to start by firstly moving, not the full collection, just the partial collection. Let me preview this off. So we're going to move it along this normal, and then we're going to extrude this curve by an amount which is going to be -2 times x. And so now we can use this to, not to trim, we can use it to split. We can split rep. You cannot, annoyingly, you cannot actually, you can't trim a solid unless the trimming, you can't trim a shape unless your cutting shape is a closed piece of geometry. So what we need to do is we need to split. Actually, let me just have a quick look. Let's see if we can split the surface. Well, let's just see if this works. This sometimes works, but not always. We'll try split these curves along this surface. Actually, that seems to have worked pretty well. And let's see if we can extract just one of them out. Let me just graph these as well. And let's see. So we're getting 2 per list. So I'll just set this to integers and then plug it in. Nope, it hasn't quite worked. So what I'm going to need to do is take an area of this geometry, and then based on the area, it's going to split my surfaces. It's going to split it up into a collection of surfaces, or 2 different surfaces per list. One is going to be much larger than the other, so I'm going to use that to my advantage. I'm going to sort all of these split surfaces according to their area, and then using a list item. Oops, I did that the wrong way. The area is my sorting parameter, and then the surface is my geometry I want to sort. And then when I pull these out, these all have much smaller areas than the rest of the trimming shape, which is why they've come out. And so now I'm going to take this I'm going to do the same thing. So I'm going to move this geometry. So it's going to move it down, and then it's going to extrude it out past the thickness, which means we can now use a trim solid. Okay, so there's my shape. I can what can I do now? I need to use my polar array now. And when I have a look at this, it should have, yep, that's what we want. Okay. I might have to pause the video while this is loading, just because it can take a while sometimes. And I don't know how this definition is going to react at the moment. So there's my shape I'm trimming. I think, let me just make sure that's the one I want. No, that is not the one I want actually. Probably want to trim this one. So let me plug this in here, and then I'll plug this in and pause the video. Actually, let me flatten this parameter first. Flatten the cutting shapes, and then plug this in. Okay, and we're back. So here's my trim solid. You can see all the tire treads have been cleaned out really nicely. You can see that that took just under a minute there according to my profiler. If you don't have the profiler turned on, you can turn that on in Display, Canvas Widgets, Profiler. Alright, so now I've got these shapes, and I've got this trimmed shape. So what I'm going to do is I'm going to extrude this, and I'm going to extrude it, let's see, where is my direction? My direction is coming from this normal vector here, so I'm going to use an amplitude. Actually, I don't need to use an amplitude, I can just use a multiplication. And I don't know how much I want to extrude this, but 10 is definitely going to be overkill, but we'll see. Let's enable that, plug that into my direction, and see how much I want to extrude. Okay. I also need to change that to negative. And maybe somewhere around 2 works for me. And so now we've got all these sort of closed extrusions. And that's almost what I want, except I do want to remove the inside of this shape here as well, because at the moment these are all closed, and so I will not be able to join them with this surface properly. So what I'm going to do is a cull index on a deconstruct brep, dbrep, and I'm going to cull out the first face, because the first face is going to be the base profile for extrusion. So when I've culled out that face, it's going to give me a whole collection of faces now. Whoops, did not want to disable that. And then I can do a brep join on those. And then I will create another polar array, plug this in, and then I can do another brep join. So for this one, we're going to need to flatten this. Actually, instead of doing that, I'll just flatten everything coming into here. Quickly lock the solver, flatten this, plug in my polar array and my trim, preview that off, can get rid of the split, can preview this on, and wait for our geometry to load. And there we go. We should have a closed brick. I can bake this out now. And there's our tire tread. Looking pretty good. So now what I will also say is I mean, okay, you could probably achieve all of this oh, excuse me, using maybe something like the boundary volume or the solid union rather than going through this sort of more tedious process. I mean, I guess I'd encourage you to try it out, see if it works for you. I just find that some of these components, like the boundary volume especially, can take, like, when I was trying to figure out how to do this definition, the boundary volume was taking in excess of 20 minutes to load the geometry. I was having similar sort of results with the solid union, and it wasn't actually even doing the right thing. So if we're sort of analytically creating every individual part and then joining it all together, Grasshopper seems to just prefer that and work a lot better, which is why I tend to do, well, that's how I tend to do my workflow. What I'm also going to do is, I mean, okay, naturally you will want to sort of be able to tweak these things on the fly to see how it's going to look, and a really great way around that is to use this data dam. So if you plug some geometry in here, we need to make sure that we break our connection over here. Let me see. So I'm going to plug, okay, I'm going to add this here, and actually let me just lock the solver really quickly. We're going to disconnect that, and we're going to disconnect that. So now when we unlock the solver, we should have nothing feeding into here that's going to be changing. Yep, I don't think so. So then now we can plug in our normal vector here and our join over here, and then I will just bring back this polar array that we created and preview that on, turn these curves off. So now you can go back to the graph mapper over here, and you can tweak these however you want. You don't necessarily need to use Bezier curves. That's just a personal preference. So I kind of want to get a bit of variation in this pattern going. So you can see this, you know, this is quite a thin one, and then we end with like a thicker one before the pattern sort of change or returns back to what it was. And then I can sort of tweak this gap a bit as well. Maybe somewhere around there. That'll do it for me. And okay, so now that I'm happy with that, I'm happy with how the sort of base tread is looking, I can come back in here, and when I hit play, all the changes that I've made are going to be fed down into the rest of the definition. And so now we have to wait, I don't know, preliminarily the profiler tells me that this should take maybe just over a minute or so. And so, yeah, I mean, this is the basic workflow that we're working with. Another reason I've sort of done this tutorial is just to show you, like, I haven't really worked a lot with the intersect methods in Grasshopper. I personally, I think I talked about this in an earlier tutorial, I personally try to avoid doing any sort of solid unions or trimming shapes or anything, because it is quite destructive to your geometry, and it's not a way that I sort of enjoy working with Rhino and Grasshopper. I prefer to work with the more sort of, well, a more sort of cleaner method of sorts, and that's what I've been trying to teach in my tutorials. But I mean, this is, you know, as long as you're doing this properly, this is still a perfectly valid way of working. So now if we bake this out, there is our finished tire tread. I hope you enjoyed this tutorial.